We are live. Welcome, everyone. So, I'm going to just start out cold with the lecture material. Then we'll have a few discussions and breaks regarding this material. Some examples for you guys to discuss in groups. I'll divide you again to a few groups and pause the recording while we do that. And I hope to get to the part in the material that we remain on schedule. So can't use too much time on chit chat here. All right, let's get back to it. So last time, the most important part maybe in some sense was the idea of what we can say about probabilities. If we had this, the philosophical issues were not that big a deal. I mean, we can discuss them later at our convenience. But the important part was here the concept of event. So you need to be able to find the unions and the unions and intersections of events, and those will always be events. And then the complement of an event is an event. So event not happening to one of two events happening, or both events happening at the same time, and so forth. And these events, not the points, but the events in the sample space are ascribed a probability measure. And the probability measure is a measure for each event. It's between 0 and 1. And disjoint events, their probabilities add up. And the whole space, you know, something happening, this P omega, that's 1. And nothing happening has probability 0. So this was, and from these basic principles, we found several theorems. I'll just go quickly through what they were. So firstly, we can add disjoint events, their probabilities. That's just straight up the axiom. We can take the probability of A when we know the probability of the complement, it's 1 minus the probability of the complement. So, you know, if you have heads and tails, if it's not 50-50, it's 20-80, then, but the point is that they always add up to 1. Right, the adding of them. So the probability of getting a 6 from a die roll is probably about 1 in 6, unless it's somehow a cheating, you know, the weighted or loaded die. The probability of not getting a 6 is then 5 over 6, 1 minus 1 over 6. Fairly simple. When the events are not disjoint, we can add their probabilities together, but we have to subtract the probability of both happening at the same time. So the probability of one of these two things happening is the probability of this happening plus the probability of that happening minus the probability of both happening. So this you have to understand. It's highly important to understand this concept. So today we will be talking about the concept that is that allows us to talk about a certain specific situation where this disjoint, sorry, not disjoint, this intersection of events, we can tell the probability by simply knowing the probabilities of the events. There are two situations when we know. We know that if they are disjoint, meaning they can't happen together, then this probability is 0. But there are other situations where it's not necessarily 0, and we either have to know this separately or we have to know one other thing. We talked already about the conditional probability. So the conditional probability was very highly important. The idea here is that we know the joint probability, A and B both happening, and we know the probability of B happening. Then we know the probability of, what is the probability that A happened if we knew that B happened. So I gave the die roll an example. So let's say the numbers are even and odd. You know, that's an event. And the numbers are big and small. And let's say big numbers are 4, 5, 6, and small numbers are 1, 2, 3. So if I know that the number was even, was it big or small? What is the probability? Well, the probability that it was small is only 1 in 3, because only 2 is the only small number that is even. And 4 and 6 are big numbers. So that's 2. The probability of it being big, if it's even, is 2 over 3. So it's just this definition 1.6 applied to this different events separately and their disjunction. So this led us to the Bayes rule or Bayes formula. We talked about that. That's highly important. We'll do a lot of exploration of this during the exercises. So I'll skip that. But the important property here was that this is actually this at the end of 24.4 page. This is usually the way we express it with just single events B and A. So the probability that B happened, knowing that A happened, we can get it from the conditional probabilities of probability of B happening, if knowing the probability of A happening if B happened, divided by the probability of A happening. So I really urge you to explore this. We'll explore this further in the exercises quite a bit. So there is numerous situations where this Bayes formula and Bayes rule comes in handy. So it's one of the most applicable formulas in this probability, and it's really helpful in your thinking. So I mean, I'm not going to say what to think about things, but I'm just going to tell you that, you know, forming opinions, for instance, or forming ideas about what's going on. I mean, let me just give an example. There has been talk about these vaccines in terms of the coronavirus and the vaccines. There was this big news somewhere that, you know, they had vaccinated some number, let's say 1 million people. I don't know what the numbers exactly were. I don't remember them, but let's say they say that they vaccinated 1 million people, and, you know, 50 people died after the you know, 2 months after the vaccination. Okay, so this gives you an idea that, okay, well, you know, this is highly probable that you will die, right? You know, 50 people in 1 million, that's 5 in 100,000. It's not huge, but it's not great, right? It's not a great outlook if you take the vaccine and you have a 5 in 100,000 chance of dying. Highly dangerous. But that's bullshit. I mean, it's complete bullshit. You know, they vaccinated elderly people. Let's say you vaccinate 1 million people who are over 70 years old. The probability of them dying during that two month follow-up period, even without any viruses, even without any vaccines, even without anything, is roughly equal to that number. Like how I said, I don't remember what the actual numbers were, but the numbers were something of this order, right? And then when you look at the probability of the person dying, who is of that subpopulation, the probability of that person dying remains unchanged if you vaccinate them. It actually goes down a bit because some of them who were not vaccinated would die because of the infection. So, you know, look, you can assess how did it affect looking at these conditional probabilities. We'll see examples of this during the examples and the exercises, and we'll talk about this. But it's really important to understand the direction of the conditional probability. I mean, what is the probability that you die if you were given a vaccine? Well, what is the probability that you die if you're not given the vaccine? What is the probability that you die in general? So this is something that you have to take into consideration, and this is something that people often neglect. And this is a way that journalists can make a really bad-looking headline, you know, headlines that make it look like something is really bad, if they don't consider the conditional probabilities. And that's something that I mean, if nothing else you learn from this course, learn this, that you should always look at the conditional probabilities. And this is not cause and effect, by the way. All right, let's just move along. We looked at this example. So the one thing that we didn't mention, I mean, the so-called Bayesian interpretation of probability. This is, again, I'm not selling this because I'm not a Bayesian myself. I don't consider it to be, you know, 100% correct idea, at least not in a puritanical way, of what probabilities mean. But the idea here is that probabilities we viewed either reasonable expectation or partial incomplete knowledge of something. So you ascribe probabilities to things because you don't know how they are exactly, but given that you know some other things, then you are able to say that, okay, this sometimes increases the likelihood of that other thing happening. I know this happened and so forth. So you formulate your ideas of probability based on what you expect of them based on your knowledge. So we can think of this interpretation that probabilities are just an extension of propositional logic, so that you know a fact to be true or it's not true. Okay, so a fact, the statement is either true or false. A person has a disease or a person has crashed their car, that's true or false, but you don't know it yet before you administer a test or something, then whether they have contracted a virus or whether they, or if they're driving during the next week, you don't know yet whether they're going to crash their car. They're just, there's just a probability there. And so you're observing things, you're not yet observing things, you're ascribing a probability because you don't know whether it's a fact or not. Be that because it's in the future or because you have not been able to observe it yet. So the idea that why we ascribe 1/6 probability to each die roll is not some magical thing that just, that we know that it's 1/6, but because we have no reason to believe, or we have no knowledge that would indicate that any of the different sides land on different, that it lands on one of the sides more likely than another. But here again, you have to understand, again, I like to take this up because I follow some of the discussions, and I'm not trying to give you any opinions on matters. I'm just telling you how to apply probability theory in terms of expectations and being critical about other people's opinions. So there were these people who said, okay, look, there is they haven't looked at this. So they looked at this vaccine, and they said that 95% of the people, let's say the contraction rate or the rate of getting a serious infection, an infection that is so serious that you really know that you're sick, getting sick, drops by 90%. So have whatever that means. Let's say that you have 100,000 people who are not vaccinated, and let's say 1,000 of them get the disease and they get symptoms, and then you administer the vaccine to another group of 100,000, and only 50 of them get, only 50 of them get symptoms or the disease. Okay, so they didn't look at any other variables. They're just this probability that, okay, the probability of getting the disease goes down. And some people say, okay, but you can still get the disease, so it doesn't affect anything. The other thing that they said, okay, we didn't look at the rates of transmission because we only tested those people who actually had symptoms. And then you say, okay, there you go, you have it, you only tested those people who had symptoms. We know that we don't know whether the actual risk of getting an infection went down. So we deduced that it didn't go down. But again, that's just bullshit. I mean, you can't deduce that. So it's just as probable that you get the disease. But that's not true. I mean, they just didn't look at it. So the point here is that if you have partial information that gives an indication to one direction, then you may not be able to say whether something happened, but you cannot deduce that nothing happened. That's just as bad. So I'm just saying, be mindful of making rash conclusions about things. And I'm not just, again, I'm not saying anything about what is true and what is not. I'm just saying about the logic of forming one's opinion. Then if you're using bias formula, use it correctly. I really do urge you to do that. It actually saves you a lot of embarrassment if you are one of those people who likes to, tell other people what your opinions are. then if you fail to use the Bayes formula, then your opinions are usually crap. Sorry about that, but you know, that's just how it is. All right. The idea in Bayes interpretation is that we have some prior knowledge or prejudice. You know, we have some idea of how things are, probability of some event. We have a prior probability, meaning that this is somehow an opinion or an idea that we formed. We encounter new evidence that an event B happened. Then we come up with this new probability for A, and it's P, probability of A on condition of B. So if you think about the quotient B probability A divided by probability B, then that's the kind of support that this B event provides for A. So if B happens and it's its probability is high to begin with. If the probability of B is high to begin with, and the probability of B on condition of A actually being true is small, then this observing of B makes you think that A is probably not very likely. On the other hand, if B has a very low probability, it's a very rare event, the probability of B happening if A happened, then is actually very high, then this gives high probability that A has actually happened. This increases the likelihood of A actually happening. This has some dangers, this line of thinking. Again, you know, think about the lottery. The Finnish lottery, I mean, there was a weekly exercise. The deadline is shortly there, but you know, if you were calculating it, it's about 1 in 20 million winning the lottery. This was way back in 20 years ago or something. Some years ago, it was still 1 in 15 million winning the lottery. So there was this person who won the lottery twice in a row. They won the lottery twice in a row. Highly unlikely. Now let's say that A is the event they cheated. What is the probability that they win twice in a row? It is very low. What is the probability that they win if they cheat? It's actually quite high. And what is the probability that they actually cheated? Well, if your prior expectation is non-zero, you know, if your prior expectation, if your prejudice that, oh, it's all rigged, if you have this prejudice, then when you observe someone winning twice in a row, you will just absolutely know that they cheated, right? Because, you know, if you say that, okay, there's about 10, I'd say there's about 10% chance that someone is cheating in the lottery. Then you observe someone winning twice in a row. Then you would have to say that, okay, if you were, let's say you were in a jury and this person was accused of being cheated in the lottery, if they won twice in a row, then you don't need further evidence. You just say that, you know, there's no reasonable doubt that this person cheated because it's so unlikely that they won. But here's the problem. They didn't cheat, did they? So this is the nature of probabilities, right? So, you know, I'm just saying that this is not doesn't help you be correct all the time. It just helps you be less wrong. All right, that's about all I have about this Bayesian rant. I'm not going to tell you more about it, but you know, look into it. It's actually a fascinating way of thinking, and I'm not, like I said, I'm not a true believer in the Bayesian truth. There are some people who really take it almost as a religious belief. All the best to them, but you know, I am less of a, I'm more like an interested layman than a true believer. All right, that's not enough about Bayesian probabilities. So let's go to the important idea of today. So another concept we need. one other concept, and this ties nicely to both the Bayes formula or the conditional probability and the ideas that we have about when I said that formula, that probability of A plus probability of B and so forth. We often have to know the probability of A intersection B. And there are two specific instances in which we know this probability of A intersection B, and there are two situations. One, when A and B are independent, which is the thing that I'm teaching you now, and when they're disjoint. And you have to understand that these two situations are not the same. Actually, they're, in all but one case, they are mutually exclusive. A and B can be independent, or they can be disjoint, but they can't really be both, barring just one simple situation where one of them is in fact zero probability, and one is absolutely certain. Sorry, one doesn't have to be absolutely certain. If one of them is zero probability, then that's independent, but that's just a ridiculous situation. All right. So we say that A and B are independent if the probability of both happening can be gained by simply multiplying the probability of A happening and the probability of B happening. We define it in this way, but really I think the best way to understand them being independent is through the conditional probability, what this means in terms of conditional probability. Because if A and B are independent, then the probability, it's the same as the probability of A under condition of B is probability of A. So observing the event A is in no way affected by observing the event B. So if A and B are independent, then we know nothing about the probability of A, even if we know that B happened. So in my case example for the odd and even numbers on a die roll and big and small numbers on a die roll, these two are not independent. When I define small to be 1, 2, 3 and big to be 4, 5, 6, because there are two big even numbers and only one small even number. However, if I let's say that I define them as very small and very big, as 1 and 2 being very small and 5 and 6 being very big, then the even, odd, and very big, very small, those are independent, because there are now the probability of getting an even number is 1/2, and probability of getting a big number is 1 in 3. Probability of getting an even big number is 1 in 6. It's 1 in 2 times 1 in 3. So they are independent. It doesn't really matter which way you like to think about this. Do you like to think about it in this way, that the probability of A intersection B is the probability of A times the probability of B, and then that this conditional probability characterization is a consequence of that? Or do you want to think about this in the way that the conditional probability characterization is the actual beef of the matter? It's the thing that you want to remember. So A and B are independent if observing B provides no evidence against or for A. That's independent. So it doesn't affect my assessment in any way. So for example, if we think that let's say that a person's, whether or not the person wears glasses has no effect on how good they are at, how good a grade they get at mathematics course, at the probability course. So I don't know. I have no idea. I don't observe whether you have glasses. It may actually be that there is some, that they're not independent, but usually we would assume that it's independent. If you wear glasses or don't, it doesn't affect your grade. Maybe, I don't know. Here are some examples. The die roll, A was 1, 2, B was 2, 4, 6. So this is small and even. These events are independent and so forth. There's an important thing. If A and B are independent, then A is also independent from the complement of B. You can prove it. It's fairly easy to prove from this set theoretical notation. It's not that important, but I mean, I understand that if it's if wearing glasses is independent of your math grade, then not wearing glasses is independent from your math grade as well. Here's the thing. We can define a set of events as independent. And this is important to understand. A set of events is independent if and only if, no matter what kind of combination you take from those events, then the probability of the intersection of that sub-collection is, in fact, the probability is multiplied. And if a set of events is independent, then every pair is independent, but the converse is not really true. And here's one that was in the examples. This was given in the exercises, this model. So we have this random experiment. We throw a coin twice. We get 1 and 0 heads for heads and tails. We take a third number to be 1 if the rolls landed differently, and 0 if they were the same. And now we have these points 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. And the probability of each of these points is 1/4. And if you look at any of these events separately, let's say event A is the X being 1, event B is Y being 1, and event C is Z being 1. Any two of these events are independent. But if you take them all, they're not independent because the probability is 0 of getting all of them equal to 1. This is actually something that is used in cryptography and things like this. I've seen actually this, I don't remember what's the name of that idea where you can hide things, hide information inside a picture. I don't remember what that's called. It's a certain thing where you can hide some information inside a picture. Well, I've seen this thing. You can do this thing fairly easily. You can create noise, and then you can create two images from a let's say use black and white image. Two images from a black-white image where you just take the noise and you take the exclusive OR so that you have these dots that are like this. So whenever there is a black dot in the original picture, you take two pictures, one where you have a 4-pixel thing where the black dots are like this, and one where they're like this. And then if it's a white pixel, then you randomly put them both either this way or that way. And then when you overlay these pictures, you can see the original picture emerge as a black and white picture. It's actually really cool because you can look at these two pictures and they look like they're completely just this white noise. I mean, I don't know if you know the old TV sets that used to have when there's nothing on TV in these old type of TV sets. Then when there's nothing on, there's just this static, this black and white static. It looks like a snapshot of that, two pictures. Then you put them on top of another and then a picture appears. And it's an example of this situation. So all the pixels seem like they're independent, but really, I mean, the whole picture there is not. So it's really a fascinating phenomenon. You should really try and understand why this is an important concept. Again, this is not something that is going to be exam material. I just wanted you guys to be aware that this independence is a very powerful concept that is used in many fields of technology and mathematics. All right, let's go through this example. So let's say that we have a device that is built from components, each labeled Ki, and they operate independently of each other. They do something, don't know what. Then there's a signal that travels through this machine from left to right. And there's an event AI, which says that this component I operates faultlessly for the time period, some time period. We observe the behavior of this machine for some time period. Let's say we look at it for a week, and we have this, each component has been tested. We know the probability of each of these components performing, functioning well for that 1 week time. So it's PI for each of these AIs. So the question is, what is the probability of the whole device functioning for some time period? We have three different configurations. One, where all the components are put in series, and the functioning of the machine is predicated on the first component does something, then the second and the third and the fourth, so that only if they are all functioning correctly, the machine will do what it's supposed to do. So another possibility, the components are functioning in parallel. So something happens, and as long as one of the components works well and does whatever it's doing to that signal, and we get an output that is fine, then the operation, the machine is considered operational. So the device operates as long as some of these, at least one of these components is operational. That's the second situation. The third situation, we have this following configuration. We have this component, M components that are put in series, and then another M components that are put in series. And then as long as one of these pipelines is working, then the machine is still working. The question is, what is the probability that this machine works correctly? So let's observe this. In the serial configuration, because they're independent, the probability of all of them working, well, you can multiply their working probabilities, because they all have to work. So it's the probability of A functioning and 2 functioning and 3 functioning and so forth, all M functioning. So we get the probability by multiplying them. In the parallel configuration, they're still independent, but you know, the probability that it doesn't function, in order for the machine to fail, all of them have to fail. In this one, as long as one fails, the whole thing fails. So we have to multiply them. In the other case, the probability of it working is the union of all of them working, right? But here we can use the De Morgan law. Again, we take the probability is 1 minus the probability of none of them working. And the none of them working is simply the intersection of the complements of all of them. And remember, because these AI are independent, the complements of AI are independent, so we get this formula. This should be familiar to you. So this is the probability that it works. It's 1 minus the probabilities of 1 minus PI multiplied. So these two formulas really, I mean, this is something that the thinking behind this serial configuration, or, you know, everything going as planned is you multiply them, and then nothing going, sorry, at least something going as planned, you know, you get this 1 minus, and then the product of 1 minus PI. So learn the difference between these two. You have to understand it and learn it. It's really highly valuable in many situations. Now, an obvious question, which of these probabilities is higher? So let's have a small break here. It says, let's have a small break here. I'm going to put you into groups. I'll have you do group work for about 15 minutes. in this case, let's say each of these pi's is about 0.5, and let's say m is 5. Calculate these probabilities in all these three cases, right? That's my question here. I'm going to stop the recording while we long. All right. So we're going to start to talk about random variables and distributions. So per se, a random phenomena, what we mean by distribution depends on how we look at this random phenomena. So if we look at it from the point of view of what's going on in the real world, and the only way we pick up information about our randomness or random phenomenon is by doing this random experiment and measuring the random value, you know, time and time again. Then what we call distribution here is you can think of it as the mathematical model of what those numbers tend to be, how they how the outcomes tend to look like. On the other hand, if we look at it from the purely from the perspective of the random variable, then what we call a distribution, you know, the mathematical model of the random variable, then what we call a distribution is basically how the way in which we can ascribe probabilities to each of these possible events. So it's like a compressed way of expressing how to ascribe the probabilities to these events. And for this purpose, we usually use what is called the density function. The density function is a function that tells you that if you have a certain point in your probability space, in your omega, then the density function gives you an idea of how much probability goes to that particular point. Because the probability of the whole sample space should be equal to 1, then you kind of distribute it. You distribute it. You distribute it among the points in your sample space. So if it's a discrete sample space, then you ascribe a probability to each of these points. But if it's a continuous sample space, you kind of smear the whole probability on that space. And in order to come up with the probability of the event, you have to resort to calculus. We'll talk about that also. There's a distinction between random variable and random value. So random variable is the model of what's going to come out of your random experiment, whereas the random value is the outcome of the experiment. You roll the die. The random variable is the mathematical object that you say that this is the random variable, and it's described by the fact that it's going to tell me something about the distributions of, you know, how the distributed the die rolls, how the die rolls are distributed. Whereas the random value is the single value that you get when you roll the die. I mean, it's the outcome of the die roll. We'll talk about this. All right. And then there's the concept of sample. A sample is something that comes out of the real world. So we observe a number of times, we observe outcomes of the random experiment, and then that's our sample. We have like 100 measurements of something. That's our sample. Whereas the distribution is like the mathematical object that tends to describe what the samples would look like if you took infinitely many of them. And now when I say infinitely many of them, I'm kind of referring to our frequentist approach. So like, it's not a completely satisfactory way of describing it, but this is one part where it's very hard to describe the bridge between the real world random phenomenon and the mathematical object that is the random variable. So I'll try to do my best here to give you an idea of how these are used best. So it's just very simple. Random variable, we can think of it as a mapping from the sample space to real numbers. I mean, you can describe a random variable by many ways, but we think of the random variable as this mapping. So we just think of this, the outcome of the sample space is the actual way, the physical configuration of the die roll. And it tells you that when the die looks like this, I'm going to give this number 1. When the die is in this, I'm going to give this number 2. When the die looks like that, I'm going to give it number 3. So we usually associate the random variable with the value, and we don't think of it as a mapping like this. But in reality, I mean, the sample space consists of things that are not actually necessarily numbers. They're just something over there, and then we ascribe a value to it. And that's the random variable, is what ascribes a value to it. So like when I say coin toss, heads or tails, and I consider heads to be 0 and tails to be 1. And then the random variable is this, the idea of associating heads to 1 and tails to 0, or the other way around. And the value is the 0 or the 1. So we can just skip the whole idea that, okay, I toss the coin, I get a 0 or 1. Random variables, we usually describe them and denote them with capital letters. So it's different from a particular value we get. And then when we get the actual value out of the experiment, we look at those with lowercase symbols, the corresponding. So X, Y, and Z. So uppercase X, uppercase Y, uppercase Z. That means it's a random variable, and it could be anything. But then it has a particular value, like 1, 2, 3, 4, 5, 6 in the case of die roll. Then we ascribe those X, Y, and Z, the lowercase letters, as you know, those are the variables that talk about the values. So just so you understand the difference between the two. Let's start with discrete distributions. They're in some ways simpler. The calculations tend to be harder, but they're usually simpler to understand. So we say that the random variable is discrete if the sample space is finite or countably infinite, meaning that the sample space contains some list of values. The list itself could be infinite, but as long as we can ascribe a natural number to each of the possible values, then we say that it's discrete. The distribution of the discrete random variable is fully characterized when we know each point's probability, each value's probability. So if we know the probability of getting X is equal to Xi, you know, the random variable getting the value Xi for each of these I from 1 to onwards, it could be finite, it could be infinite, then we know what the distribution is, right? The distribution is nothing else but just the probability, knowing the probabilities. So we know the distribution if we know the probabilities of each of these points. So how do we describe them? A very common way to describe them is by use of a probability density function. So the probability density function is a mapping from real numbers to 0, 1. And now in real numbers, we go through not the random variable, but the values of the random variable. So we take a value of the random variable, and each value is ascribed the probability of that value being the result. That's greater than or equal to 0 for all X in this real numbers. And then whenever X is not a value in your sample space, then obviously it's 0. So the sum of all values within the sample space, the function is taking the function and adding those numbers together is 1. And for each particular value X, f of X is actually equal to the probability of the random variable having the outcome of this X lowercase x in this case. So for example, in the case of the die roll, we would have the probability density function where f of 1, f of 2, f of 3, f of 4, f of 5 and f of 6 are all 1 over 6. And for all other possible values, it's 0, obviously. That this would be the density function for the diroll. Sometimes this probability density function can be called the pointwise probability function, because, I mean, in the case of discrete variables, the function actually gives you the probability of each point. It's a bit different from for continuous variables, but for discrete variables, this is the way we can think of it as the pointwise probability function. And it's fairly easy. If we have an event A, then it's simply a subset of the sample space. Then we get the probability of A by adding the function's values for each point in A. So it's simply, you know, add all the pointwise probabilities in the set A, and you get the probability of getting A. I'd say here, please verify that the Kolmogorov axioms are satisfied. It's fairly simple to do this. I mean, these guarantee this because they add to 1. Obviously, it's between 0 and 1. It's non-negative, so it's obviously there any sum in that situation is non-negative between 0 and 1. And because the set of all subset of this sample space is a sigma algebra because it's a countable set, then we can get the other Kolmogorov axioms to be satisfied. So there's no problem here. Here's an example. Let's take the random variable with the sample space of positive real numbers, positive integers. And let's ascribe to each point the probability 1 over 2 to the power of x. Please verify that this is a proper probability density function. This is a example that I will ask you shortly to do in groups. Calculate the probabilities of the events x equal 4 and the conditional probability that x is greater than 2 under condition that x is smaller than 4. So this is an exercise that I'm asking you guys to do shortly, but we'll look a little bit forward. In addition to this random variables probability density function, we often define a cumulative distribution function. Not in all, this doesn't make sense in all sample spaces, but it makes sense when we have the sample spaces are ordered in some way, in such a way that it makes sense to talk about you know, the order x is smaller than or equal to something. Usually we do have a mapping into real numbers such that this makes sense, but it doesn't necessarily have an intuitive or any reasonable interpretation. But for instance, if we're playing a game of chance where you have to move your pawns or pieces, you know, some number of steps and you roll the dice, then obviously in some situations like this, you know, who gets furthest within a certain number of rolls and something like this, then in this case is the cumulative distribution function it makes sense. But it's not necessarily, cumulative distribution functions are not necessarily that informative in all cases. But however, in the real life examples where we are measuring some quantity that is clearly ordered, like height, weight, something like this, salary, something like this, then it's a very commonly used tool. And you can define it as, you know, the probability of the event that you get a certain number or smaller. And then it's simply, you add all the values from your sample space that are smaller than or equal to x, and you get this cumulative distribution function at x. This is much more fascinating and much more informative when we have a continuous variable, and then this has a lot more use than in discrete variables, but it has some uses in discrete variables as well. Again, the cumulative distribution is obviously not continuous in the case of discrete variables. It is continuous when we talk about continuous variables, but we'll get to that. We'll burn that bridge when we get there. Sorry, I'm a fan of malapropisms. Okay, so obviously the limit at minus infinity is 0, regardless of the sample space. I mean, if it's 0, if it's like a die roll, the numbers are between 1 and 6. And the probability of getting something smaller than or equal to 0 is obviously 0. So anything smaller than that, it's just 0. And likewise, you know, the limit at infinity is 1. But again, like in many cases, like with the die roll, the probability of getting a number smaller than or equal to 10 is 1, because all the numbers are between 1 and 6. The probability of getting a number between two values A and B is easy to calculate with this, because it's simply f at B minus f at A. And here you have to understand that this does not include the point A, because this is the probability of getting smaller than or equal to A, and this is probability of getting smaller than or equal to B. So this removes the probability of actually A also included in this f of A. So if we calculate the random variable from the previous example, then we can calculate its cumulative distribution function. Fairly simple. All right. Now, where was I? That's the question. Let's do this example 2.2. I'm going to stop the recording for a while, and I'll give you guys 5 minutes to do that. Okay, so I had a question which was fascinating and really, I mean, I want to clarify this. So it's very good that this question arose. So the question was, where do we get this? I'm going to do an annotation here. So can you see my drawing here? So I'm underlining. Can you see that underline?
No.
No, it's not again. Okay. I have to do this share in another way. So I'm sorry. I have to do just a very quick, it seems like this is somehow unreliable. So I'm going to share the whole desktop. So now you should be able to see when I do this. So here was f of x, right? Now you can see it, right?
Yes.
Yeah.
Yes.
So the question was, what is this x here? Where do we get this small x here, or this lowercase? So I said the convention of notation is when we have a random variable, in this case, it's the capital X here. That's our random variable. Then the random variable is the process by which we get these different values, 1, 2, 3, 4, 5, 6, so forth. And then we use a lowercase x, in this case, this lowercase x, to define or to refer to this particular values. So for each particular value, be that 1, 2, 3, 4, so forth, this f of x, which was the PDF or the probability density function, it's defined as 1 over 2 to the power of x. So please verify that this is a proper PDF. I didn't do that, but what you need to really verify 3 things. No, 2 things. That it's not negative, and the sum of all of these is 1. Sum over the sample space. Okay. Now the question before you in the group was that what are the probabilities of the events that x is equal to 4, and then the conditional probability x is greater than 2, under the assumption that the probability is less than 4. Now I ask you guys to drop your answers in. If you had the answers, and if you got the answers there, then drop them in the chat box. If you will for each group, and then we'll discuss these. So what is the probability that X is equal to 4 in this case? It's fairly simple, just a simple question. Well, like I said, it's often referred to as the pointwise probability function. And in this case, it's easiest to think of this as simply giving the probability that X is equal to 4. So that's 1/2 to the power of 4, because that's the value, right? 0.0625, or, 1/16, if you will. That is correct. What about the conditional probability that X is greater than 2 under condition X is smaller than 4? So basically you have to calculate the probability of getting X greater than 2 under X smaller than 4. So the suggestion is 0.125. Anyone else? Someone got 1/7. Okay, let's do this. Let's do this math here. Okay, so I'm going to just, what cases does this refer to? Well, the possible cases of X is smaller than 4 are the cases 1, 2, and 3, right? And of these, the only possibility is X equal 3. So the raw probability of X, so the probability, yes, yeah, there are a lot of suggestions, all of which are very nice. So the probability, oh, sorry, luckily you didn't pull the plug here. So I'm just going to do it with pen and paper. I'm doing pen and paper, so let me just do this pen and paper. I think it's good old fashioned pen and paper here. So we have 4 possible cases, right? We have we'll do this with us. So we have this probability of X greater than 2 under condition X smaller than 4, right? So what is the conditional probability? Well, the conditional probability is simply the probability of X greater than 2 intersection X smaller than 4, right? Divided by probability of X smaller than 4. That's the conditional probability. Looking further, X greater than 2 and smaller than 4, there's just one case. That's probability of X equal to 3 divided by the probability of X smaller than 4. That comes directly from the realization that there's only one value that has this, it's X equal to 3. So probability of X equal to 3, it's just 1 to the 2, sorry, 1/2 to the power of 3 divided by, well, there are 3 cases of X smaller than or equal to 4. So that's 1, 2, and 3, right? So there are 3 cases. So that's 1/8. So we calculate this. So this would be 1/8 times, and then there's going to be 1/2 is let me just think. What is 1/? Yeah, sorry. I'm holding it up. I'm just calculating this now. I just want to make sure that this is correct. So that's going to be 4/8 plus 2/8 plus 1/8, and then the 8s cancel out. His 8's cancel out, so that's going to be 1/7. Like someone said here, that's 1/7. That's correct. So the answer is 1/7. Let me just show it to you one more time. So the probability is 1/7. So there you have it. Don't worry if this was hard to you. We'll go through these in the exercises, but you know, this is something that you might want to know how to do. Okay, let's carry on. So here's the cumulative distribution function. Let's look at some particular distributions that have these nice properties or that are discrete and that we will be using. Discrete uniform distribution, if we have a n sample space, a finite sample space, then we could have what is called a uniform distribution. A uniform distribution meaning that all of the points have the same probability. So an example of a uniform a uniform distribution is one that arises when you have a die roll, for example. We assume that the dice have equally probable, also landing on each side is equally probable. So that is an example of a discrete uniform distribution. The question is, can you have an infinite distribution that is discrete? Think about this at some point. Not going to spend time on it now, but think about it. We usually write it like this. We have some kind of a shorthand for each. So UD is often used for uniform distribution, or U also. So in this, we use this tilde or this worm, what do we call that, to indicate this X conforms to or X follows the uniform distribution between A and B. So in the uniform distribution, there are all the values between A and B, and they're equally probable. And it has a probability density function of 1/b minus A plus 1, if this is in the case of when there are consecutive integer values. This is the most common situation where we have a uniform distribution. But mind you, the uniform distribution is uniform if it's, the distribution is uniform if each point has equal probability. It doesn't have to be like integer values. It can be like an apple, orange, and a pear, and then they each have probability of being picked as 1/3. So it doesn't mean that they have to. We deal with numbers usually because they're easier to operate with. An example which I already mentioned: the 6-sided die has the uniform distribution between 1 and 6. And it has the density function 1/6. Here's an example. We have n items in the box. We have m of them are of type A. So let's say that there are apples and oranges, and we have m oranges. There are capital N fruits, and lowercase m of them are oranges. We pick n, so we pick some number of items from the box without putting anything back. We define the random variable x as the number of oranges we got when we picked. And we should determine the distribution, so pointwise distribution of this random variable. So this is going to be what is known as the hypergeometric distribution. This is a very common occurrence in combinatorics. So I just thought, how do we derive this? We start with classical probabilities. So let's start with this equally probable. Each piece of fruit coming out of the bag is equally probable. So if they're apples and oranges are roughly the same size, oranges tend to be a bit bigger, but let's just think that apples and oranges, they're of the same size. So it's equally probable of getting each and every one of those fruits that we take from the box. So if we pick items, what are the constraints here? If we pick any type A items, then the number of items that we get cannot be smaller than 0, obviously. Also, we cannot get more type A items than we actually pick. Also, we can't get more type A items than there actually are in the box. So this is X must be smaller than or equal to N, but it must be also smaller than or equal to M, whichever is smaller. So let's say that we picked X items of type A. We are looking, remember, we are looking for the probability of our result being actually X. Then we picked up at the same time N minus X items that are not of type A. So we picked N items, X of them were type A, so N minus X are not of type A. Now, how many different ways are there of picking X out, given that, let's say that we pick those apples and oranges separately, and we're picking X oranges out of M different possibilities. So that's M choose X. So that's how many different combinations of particular oranges there are that we could have picked when we picked X of them. On the other hand, we picked N minus X apples. And there are capital N minus M apples, because there are N fruit, M oranges, N minus M apples. So it's N minus M choose N minus X apples. So the product rule gives us that how many ways we can pick X oranges and N minus X apples can be gotten by the product of N minus M choose N minus X times M choose X. This comes from the product rule. There are this many ways in which we can pick X oranges and the rest are apples. Now, just picking up any N objects from that bag is simply capital N choose N. And this many are a situation in which we picked up exactly X oranges. So given that X is smaller than N, and obviously also smaller than M, then the probability of picking X oranges can be obtained by this product N minus M choose N minus X times M choose X divided by capital N choose N, because that's the number of ways in which we can pick N objects. It looks complicated, but it's not actually. If you learn this way of thinking, then I think this is a nice example of a distribution that if you figure out how this exactly goes and how this is done, I'll put a few examples and exercises in the exercises. Then many seemingly problematic combinatorial problems can be actually understood by this way of thinking. So that's why I think this is a nice example. So we define this as what is called the hypergeometric distribution. It has 3 parameters: how many items there are in the box, so total, how many of the items in the box are of the type that you're counting, i.e. in our example, oranges, and how many do you pick. And the sample space is obviously consists of whatever is bigger, 0 or N minus capital N minus M. This is because it may be that it's constrained to this number. This means the situation where you pick so many that you have to at least pick 1 orange or at least this many oranges. Because if there are, let's say there's 8 oranges and 2 apples, and you're going to be picking 5, then you're going to have at least 3 oranges. On the other hand, X must be smaller than the minimum of the number of, smaller than or equal to the number of items there are. You know, if there are three oranges there and you pick 4, you cannot still get more than 3 oranges. And if you pick 3 and there are 5 oranges, you can't get more than 3 oranges. So that's where this minimum comes from. This is our sample space of the hypergeometric distribution. It's fairly simple to calculate, but I think what is most to be learned from this is the way you set up this distribution. So it's actually very cool. So we'll have some example with donuts and croissants or something like this. I like food, pastry, I like fruits, so that's. There's one example with balls, 5 white balls, 7 black balls, a total of 12 balls. And this calculation of hybrid results in we pick 6, and we get the probabilities here calculated. What is the probability? Yes, at least 4, so 4 or 5 and so forth. All right. One more example. A course has 5 different topics, and there are 4 questions in the exam. You can learn all 5, and or you can learn some number of them. So 250 students study for the exam by studying only two topics perfectly, and they just disregard the last 3. The person passes the course by answering half the exam questions correctly. How many students would you expect to pass the course in the first exam or not pass the course after taking 3 exams? Don't try to calculate the actual numbers. Try to set up it in terms of hypergeometric distribution. So I leave you to do this example, and we have this. I think we have this in the example material for next week. I'll publish the model answers and the model results, and you can look at them independently, because we don't have enough time to go through all the calculations here. All right, I'm going to stop at this point here for this. We continue tomorrow from the so-called Bernoulli distributions and geometric distributions and derivatives of what we call the Bernoulli distribution. I'm not going to say have you learned it, but there's going to be geometric distribution, there's going to be binomial distribution and so forth. So we'll talk about those shortly. But I'm going to stop for today. You have about 5 minutes to ask questions. I'm going to stop the recording.